Hello viewers, continuing with our series on probability, today we will be discussing multiplication theorem, leading to also discussion on dependent and independent events. In our previous lesson, we talked about concept of conditional probability. What is the probability of event E happening knowing that event F has occurred? We also looked at a relation which can be used as a formula. The result that we discussed and derived was that the probability of E given that F has occurred is same as probability of E intersection F divided by probability of F, where probability of F is not equal to 0, that is F is not an empty set, it is not an impossible event. At the same time, probability of F given that E has occurred is same as probability of E intersection F divided by probability of E. So, when we look at probability of E intersection F, it is nothing but probability of E and F. In a situation like this, where it says what is the probability of getting a sum of 7 given that one die shows a 5, an example that we discussed earlier as well. If I know that one die shows a 5, then these are the 11 possible outcomes. Out of these 11, there are 2 cases in which a sum of 7 is also satisfying. So, that means these are the 2 possible outcomes in which E and F, both conditions are being satisfied. What we have is the formula, that is P E given that F has happened, leading to a result which says that probability of E and F would be same as probability of E given that F has occurred into probability of F. In other words, this is what would be true also if rewritten as probability of F given that E has occurred into probability of E, and this is exactly what is referred to as the multiplication theorem, which allows us to find the probability of E and F as the product of probability of E given that F has occurred into probability of F, same as probability of F if E is known to have occurred into probability of E. Of course, we go with the conditions that probability of F and probability of E in such discussion is non-zero. Let us consider an application of what we just looked at. The problem states that 2 balls are drawn at random with replacement from a box containing 12 red and 8 green balls. Find the probability that both balls are red. First ball is red and second is green. Emphasis is on with replacement. You will understand why it has been put in bold for you. If I say R is the event of getting a red ball, G getting a green ball, then I want to find the probability that both balls are red, that is R and R. In language of sets, it can be written as R intersection R probability. By the multiplication theorem, it should be same as probability of a red ball into probability of red given that a red ball was drawn. In this case, we have 12 red balls. So, the probability of red would be 12 by 20, and in this case, since the second ball was drawn after the first was put back in the box, the probability of the second red ball remains 12 by 20, and that simplifies to be 9 by 25. So, if I have first as red and second as green, then the probability would be probability of R and G, which is probability of R into probability of G given that R has happened, results in 12 by 20 into 8 by 20. The total possible outcomes are 20, 8 are favorable for green, simplifies to be 6 by 25. Now, if I change the problem and say it as 2 balls are drawn at random without replacement, which is normally the understanding if nothing is said, the question just says two balls are drawn successively from a box, then it would simply mean that first is drawn, notice the ball is kept out. Such cases would be without replacement. I have 12 red, 8 green balls. What is the probability that both balls are red? In this case, again starting with the same notation of R and G, probability of R and R, which is probability of R intersection R, will be probability of R into probability of R given that R has happened. That is what the multiplication theorem tells us. Probability of R red ball is 12 by 20. Probability of R given that first was red will be 11 by 19. 11 by 19 because one red was taken out. 19 out of 20, one ball gone leaves us with 19 possible outcomes. This calculation simplifies to be 33 by 95. Second situation was, what if the first is red and second is green? In this case, again by multiplication theorem, I have probability of red into probability of green given that a red was taken out. Red probability is 12 by 20. What is the probability of a green ball given that red taken out? 8 favorable for green, but the total number now has become 19, and therefore, probability of green given that red ball was taken out will be 8 by 19, and that simplifies to be 24 by 95. So, what you have observed in this case is that since the ball was not put back, the probability of the second ball gets affected either because of the total number that has got affected, or in the previous case the favorable number has reduced. This is what we are interested in as independent and dependent events. The first category was of independent events. Two events E and F are said to be independent if probability of F given that E has happened is same as probability of F. That is, the probability of a second red ball given that first was taken out remained same as the probability of the red ball when the balls were put back after the first draw. Or if in this case, as you can see, probability of E given that F has happened is same as probability of E, provided probability of F is not equal to 0, then E and F are said to be independent events. In such situation, we can also use the multiplication theorem as a test. If probability of E intersection F is same as probability of E into probability of F, then the events E and F are said to be independent. So, this works out as a good working rule as well. If you find out the individual probability of event E and event F, multiply them together. If it results in the same as the probability of E and F, then the events are independent. Let us consider an application of what we have discussed just now. The problem says that a die is thrown. If E be the event, number appearing is a multiple of 3, F the number appearing is even, then find whether E and F are independent. So, if we start with the event E in the roster form, number appearing is a multiple of 3. So, 3 and 6. F number appearing is even. So, 2, 4, 6 are favorable for F. We want to check whether E and F are independent. So, let us find the probability of E and F, which is 1 by 6. There is one element which is common in E and F, and total possible outcomes was 6 when you throw a die. Probability of E independently as calculated is 2 by 6 and probability of F is 3 by 6. So, probability of E and F is same as probability of E into probability of F, and that confirms that E and F are independent events. So, the result that we just saw earlier can come in quite handy to establish whether two events are independent. And thus the result that we established earlier comes in quite handy to decide whether two events given to us are independent or dependent. Let us consider another application. Here the problem says that a bag contains 5 white and 3 black balls. 4 balls are successively drawn out and not replaced. What is the probability that they are alternately of different colors? So, if I take W to represent a white ball, black is represented by B, then we get balls alternately of different colors in the order WB, WB, or I can start with the black. So, black, white, black, white. So, to find probability of balls of different color is same as finding probability of WB, WB or BW, BW. This can be written same as the sum of these probabilities by knowing what we call as addition theorem, and also keeping in mind that A and B, if they are exclusive, mutually exclusive even, then probability of A union B is nothing but probability of A plus probability of B. So, here you can get either the first order of balls or the second, that is these are two mutually exclusive possibilities, and therefore, the probability would be the sum of the two probabilities. Further, probability of white black can be written as the product using the multiplication theorem, product of probability of a white ball, which is 5 on 8, probability of a black ball. There are 3 black balls, but the balls are not replaced. So, the total outcome becomes, the total possible outcomes remain now 7, and therefore, the probability of the second ball being black is 3 by 7. Third ball being a white ball, probability will become 4 by 6, because one white has gone and one is less from the total, into 2 by 5, remaining balls are 5 and there are only 2 black balls left. Similarly, we can find the probability of black white, where we start with black 3 on 8, white 5 on 7, then black 1 less and 1 total less, remains 2 by 6 into 4 by 5. Simplify to get the probability of 4 balls of alternate colors. Along with what we have discussed so far, we also have few small results which are quite important and useful as we take more applications. The result says that if E and F are independent events, then E and not F are also independent. Not E and F are independent, not E and not F are also independent events. Let us see how we are going to use this in our next problem. The problem states that probability of solving specific problem independently by A, B and C are 1 by 2, 1 by 3 and 1 by 4 respectively. If all three try to solve the problem independently, find the probability that exactly one of them solves the problem, and second part says the problem is not solved. So, again if you define A, B and C to be A solves, B solves the problem and C solves the problem, then we know what P of A, P of B and P of C is. Correspondingly, you can find what is the probability of A not solving the problem, 1 minus probability of A. Similarly, for probability of not B and probability of not C. Now, we want to find the probability that exactly one of them solves the problem. When you say one of them solves problem, it means that if A does, then B and C do not solve the problem, and therefore, we have the situation described as probability of exactly one solves the problem to be same as probability of A, B naught, C naught, or A does not, B does and C does not, or A does not, B does not solve, but C does, all three mutually exclusive. So, by addition theorem, it results in the sum of these three probabilities. Again, as we saw earlier in that list of results, if A, B, C are independent, so is A and the B complement and the C complement. Therefore, probability of A, B complement, C complement turns out to be the product of the three probabilities. Similarly, for the other two cases, and therefore, we have each one of them replaced by their corresponding value, which all simplifies to be 11 by 24. The second part says find the probability that the problem is not solved. That means A does not solve, B does not solve and C does not solve, which would be same as by the result. If A and B are independent, so are their complements. Same as writing probability of not A into probability of not B into probability of not C. So, putting the value of each individual probability, it simplifies to be 1 by 4, and therefore, probability of the problem not getting solved is 1 by 4. So, this is what we have as of multiplication theorem and the concept of dependent and independent events. I hope this has helped you in clarifying certain concepts. Pick up a book, try some more problems and check if it has helped. Thank you so much for watching the show.